more concepts on chapter 11 that are not covered in the main chapter but are given as an appendix. The first definition that we are going to look at is convex. A function f is called convex on an interval I on an interval I if for every a and b in the interval, for every a comma b in I, the line segment joining a comma f of a and b comma f of b lies above the graph of f. Lies above the graph of f. Okay. Now, you might think that this definition is not very mathematical in a way. What does lies above the graph of f mean? I mean, on a picture we can see this. Like, this is my graph of f of x. I take point 1 here, point a, b, f of x, f of a, f of b. I'm sorry, f of a, f of b, f of a. And in a picture, I can be like, okay, yeah, this is what it means by lying above, but what does it mean by lying above in a general, proper mathematical sense? And so the proper mathematical way of defining it would be a function f is called, well, is convex, or alternately concave up on an interval I if for a comma b comma x in I with a smaller than x smaller than b, so that x is between a and b, we have well, technically it should be maybe, let me just say, for every a comma b comma x and I with this, we have f of x minus f of a over x minus a is strictly smaller than f of b minus f of a over b minus a, right? So this is more or less saying, oh, if I take the limit of f of x, this is going to be the slope of the tangent line at a. This is saying that every secant line for everything above bigger than a should lie above the tangent line. Okay, and that is more or less our first major theorem. So a function similarly is called concave down or concave on an interval I if the inequality is exactly reversed. So maybe before theorem, let me do that. Definition: f is concave / concave down if f of x minus f of a over x minus a is greater than f of b minus f of a over b minus a for a, b, x as above. Okay, so then theorem: let f be convex. Let f be convex if f is differentiable at a, if f is differentiable at a f is differentiable at a, then the graph of a, graph of f lies above the tangent line at a. Tangent line at a, except at the point a itself, a comma f of a, where the tangent line does touch it. Okay, and if b is greater than a and f is differentiable at b, both a and b, f differentiable at a and b, then f prime of a is smaller than f prime of b. Okay, so this theorem is more or less giving you the same idea as what I said before, that if I look at the definition of convex, f of b minus f of a is bigger than b minus a, so the secant line lies above the tangent line. But the only way the secant line is lined above the tangent line is if f of b actually lies above the tangent line, right? So proof: if 0 smaller than h1 smaller than h2, then it is easy to see that f of a plus h1 minus f of a over h1 is strictly smaller than f of a plus h2 minus f of a all over h2, right? Because, well, that is my definition of convex. And therefore f prime of a, which is the limit as h goes to 0, is smaller than f of a plus h minus f of a over h for every h greater than 0, right? And that means the secant line is above, therefore secant line is lies above above the tangent line, and therefore, well, the only way the secant line lies above is if the endpoint of the secant line is above. Therefore, f of a plus h lies above the tangent line, right? Similarly, you can see that if I take h2 smaller than h1 smaller than 0, then this situation is exactly reversed. F of a plus h1 minus f of a over h1 is now going to be bigger than f of a plus h2 minus f of a over h2, right? Because f of a plus h1 is actually bigger than f of a plus h2, and therefore that means that the slope of the tangent line, which is f prime of a, is going to be bigger, not smaller, bigger than f of a plus h minus f of a over h for every h smaller than 0. Did I miss greater than 0 here? No. Okay. So it is greater than the slope, and therefore f of a plus h, again, since this is going now in the negative direction, lies above the tangent line for every h smaller than 0, and therefore, since it's true for h greater than 0, for every h greater than 0, h smaller than 0, therefore f of a plus h lies above the tangent line for every h. Okay, well, maybe not equal to 0. Great. In terms of an image, if you guys are having trouble imagining this, think of a convex function like this. Maybe this is my tangent line here. A secant line is going to look like this. If my h is negative, it's going to look like this. If h is positive, both of these points are lying above because the entire secant line is lying above. And so, obviously, it has to, both of these points have to lie above the tangent line. That proves the first part of the theorem. Now, to show part 2 of the theorem, I can say that, well, f prime of a is smaller than f of a plus b minus a minus f of a over b minus a, which is to say, therefore, f prime of a is strictly smaller than f of b minus f of a over b minus a, right? By the exact same logic, however, f prime of b, so this is from part 1, and this is from part 2 of the proof, f prime of b is bigger than f of b minus f of a. Let me write it like this maybe. F of b plus b minus a plus a minus b minus f of b over a minus b. So a minus b is negative if b is greater than a. So this is equal to this, which implies, therefore, f of b is greater than f of a minus f of b over a minus b, which is exactly equal to f of b minus f of a, f of a over b minus a. And therefore, using that as the middle term, I get f prime of a is strictly smaller than f prime of b as required. Okay, I'll stop this part here. We'll look at some lemma and a couple more theorems in the next part.